Hello everybody, we're going to continue our lesson on section 18G, which is about integration by substitution, and we're going to look at a few examples. So first, we're starting with an expression like this. So it looks like there's some kind of product, like we've got a product of two functions, this one's raised to an exponent, and we're kind of confused. If you see something of this form, start by taking that part that's being raised to the exponent and call that u. So we're going to let u be x squared minus 1. Then I can take the derivative of x squared minus 1, which is 2x, and I can isolate for dx. Now I can rewrite this function, okay, and I can replace this x squared minus 1 with u, so that we get u to the 6, sorry about that. And I can replace this dx with du over 2x. And that allows me to cancel out this x term here with the x in the denominator, leaving me with 1/2 u to the 6 du. That is something I know how to integrate. I start by pulling that 1/2 out of the integration sign, out from the integration sign, taking the integral of u to the 6, which we now know is u to the 7 over 7. I tidy it up by multiplying my two fractions together, and I include my plus c because I don't have enough information to figure out what c is. Okay. I also remember to replace that u back with the x squared minus 1 that I changed it to in the first place. For example 2, this is a little bit more complex. We have 3x over x squared plus 2. If we rewrite this with a negative exponent, the denominator, then this looks more like this form that we saw here, a product of two functions. I'm going to let the part that's being raised to the exponent be written as u, and I'm going to take the derivative of u, which is 2x. Okay, and if I isolate for dx, I'm going to get du over 2x. Now I can take this original function and I can replace this x squared plus 2 part with u. So I get u to the negative 1. And I can replace this dx with dy over 2x. That will allow me to cancel out these x terms and have an integration, a function to integrate, I should say, that's all in terms of u. Now, I can pull out any constant factors like 3/2. I can take the integral of u to the negative 1. Remember that is not the power rule. That is, that's ln of u. And I can add that plus c. Last thing I'm going to do is remember to replace the u back with the x squared plus 2 because my original question had to deal with x's, not u's. Okay. And we're going to take a look at two more examples. This first one is very similar to the ones we've already done. The only thing is you might not be sure which one should I substitute u for. And I'm going to suggest that you always pick the one that is being raised to the exponent. Okay. Also, we notice that if I took the derivative of this expression, I do get 6x plus 5. So I chose 3x squared plus 5x to be u. I took the derivative, and indeed I got 6x plus 5. I isolated for dx. Then I substitute. Instead of this expression, I replace it with u to the 4. I keep the 6x plus 5, and I replace dx with du over 6x plus 5. I end up with the integral of u to the 4, which is 1/5 u to the 5 plus c, and I remember to replace that u to the 5 with 3x squared plus 5x. Okay. In our last example here, we have a radical function, and the big trick here is just to remember to rewrite that radical as a rational exponent. That's the part I'm going to let equal u. I'm going to take its derivative and isolate for dx. Then I'm going to do my replacing. So I'm going to replace this x squared minus 3x with the letter u, or the variable u. I'm going to keep the 2x minus 3, and I'm going to replace dx with du over 2x minus 3. Now I can cancel out those factors of 2x minus 3. I'm left with u to the 1/3 du as my integral. And remember that I add 1 to the exponent and I divide by the exponent plus 1. When I divide by this fraction, I multiply by the reciprocal, and I replace that u with the x squared minus 3x from above. Don't forget your plus c to indicate that there could be a constant that we have not yet figured out. And that is it for integration by substitution. Thank you and have a great